Hello, welcome to my classroom. I know that it's a long time since I last uploaded my lecture, but it was unavoidable. I apologize for that. Anyhow, continuing with the topic of soil water, today we will discuss soil water evaporation. In fact, evaporation is a very important component. You know that this is a very important component of hydrological cycle. Whether evaporation is taking from the free water body, or it's taking from soil surface, or it is taking from plant canopies, because this is how the water evaporates, goes up into the atmosphere, condenses over there, then the clouds are formed. Again we receive this moisture in the form of rainfall, precipitation, snowfall, etc., and again the process goes on. This is how the water cycle moves. So that's why it's considered to be a very important component. But still, the most important is soil water evaporation, because soil water evaporation is important from two things. One is because of evaporation, the plants, they grow in soil, and once the evaporation is taking place from the soil surface, soil becomes dry. The root zone that becomes comparatively dry, I should say. Ultimately, if the evaporation rate is high and the plants or soil does not get any water in the form of irrigation or rainfall, then the moisture may decrease up to the extent that the plants may start drying up. At the same time, the evaporation is also taking place from the plant surfaces. So this is one thing, that there could be dearth of moisture in the soil because of evaporation losses, and ultimately plants may suffer, crop yield may suffer. Second most important point regarding soil water evaporation is the formation of saline soils. It could be saline alkali or alkali soils. It is again because the salts, the salts or solutes, they get dissolved in water, and when water from the lower layer, it rises to the surface because of that capillary pull, because of the evaporative demand of the atmosphere. So at the surface, the moisture gets evaporated, and the salts, they are left behind in the surface layers, in the root zone, thereby affecting the plants, and ultimately leading to formation of saline soil. So these two components are very important when we talk of soil water evaporation. Now today in this lecture we will study that what is the mechanism, what is the process of water evaporation from the surface of soil. But before we discuss actually the evaporation from soil surface, let us just review ourselves that how evaporation takes place from a free body surface. So here, this is a free water surface. So you have free water over here. It could be a pond, it could be a lake, it could be a river, it could be simply the water flooded on the surface of the soil. So now here you know that the water molecules, water is formed of the molecules, water molecules, and those water molecules are in continuous motion, and those water molecules are attracted on all the sides. For example, if you have a water molecule just at the surface of water, so it will be attracted on this side, it could be attracted on this water molecules, because this is surrounded by the water molecules and they are attracting this water molecule, and this force of attraction is directly proportional to the masses of the two water molecules. Mass of water molecule 1 attracting another molecule 2, and it is inversely proportional to the scale of the distance between two water molecules. If this is another water molecule, this will be distance, this will be m1, mass m2. So directly proportional, this force of attraction will be directly proportional to the masses of the two particles, inversely proportional to the scale of the distance. So more the distance between the two particles, lesser will be the force of attraction. Similarly, if the two particles are heavier, or the mass of the product of the mass of two particles is high, then the force of attraction will also be high. So this is how that this water is formed of different water molecules which are in continuous motion, and they have some, because they are in motion, they have some kinetic energy, and due to temperature, due to heat energy, this kinetic energy increases, and this increase in kinetic energy, so that means if a molecule has high kinetic energy, it will try to jump out of this surface of the water or out of the water body, and again, so the water molecules, they will concentrate over here just above the surface of the water. So we call this as laminar layer. So laminar layer is where the water molecules, they have higher kinetic energy, they get evaporated, they get transformed from liquid to vapor form, and they get concentrated. Now the question is, again here just above the water surface, the concentration of such vapor molecules of water, that is higher. Now the question is, sometimes what happens that if its kinetic energy increases, it jumps out of this water body. But again, due to attraction of the water molecules, some forces, so there is negative force, so their kinetic energy may decrease, and it can come back into the water. So this happens. So some molecules, they jump out, and again they come out. Now actually it depends upon how much kinetic. If this kinetic energy of the molecule is higher than the force of attraction by the adjacent molecules, then this molecule, here the concentration decreases, then this molecule, it comes over here. So once it is out of the laminar layer, we call then this will be sort of zone of transition. So once the molecules come over here, then if you have, then at the surface we have some turbulent layer. Turbulence is created when wind blows. So when air blows, we call it as wind. So due to wind, these molecules, they are carried away. So once they are in the turbulent zone or turbulent layer or turbulent zone, you can see, the molecules, they get evaporated. Then there's very little chance that they may come back into the water body. Now the question is, if there is no turbulence, in case of no turbulence, then what will happen? The water molecule may not be carried away, by the air, because there is no air, there is no turbulence. So water molecules may not be carried away, they remain concentrated over here. So ultimately, the zone of transition and laminar layer, this will become saturated. So here the vapor pressure, and vapor pressure, it is the partial pressure of the water molecules in the air. So vapor pressure over here of this transition zone or turbulent zone, this may become equal to vapor pressure of this laminar layer. So when the two vapor pressures are equal, so vapor pressure of laminar layer, this becomes equal to vapor pressure of layer above it. And this will happen when there is no turbulence. Then there will not be any evaporation. Then in this case, no evaporation will be there. Or in other words, sometimes it could be condensation, because if the vapor pressure Ultimately the vapor pressure may increase over here in this layer and it could be low over here. Then the reverse may, and reverse of evaporation is called as condensation. This is why you get dew during the night hours. You have formation of dew on the grass surfaces, you can see it. So I hope the things are clear now that how evaporation takes place. So for what we understand from this, for evaporation to take place, we require two things. So this evaporation rate, or rate at which evaporation will take place, whether it is slow rate, it's taking place at a R rate, this is equal to the product of resistance and the driving force. Now, what is the driving force? Driving force is only if there is difference between the vapor pressure of the laminar layer and the vapor pressure of the layer above it. This is called as, this driving force is vapor pressure gradient, or we also call it as vapor pressure deficit. So whether it is vapor pressure deficit or vapor pressure gradient, it is one and the same thing. Only thing is that this vapor pressure gradient is difference in the vapor pressure of the two layers. One is laminar layer, one is layer above it, and only per unit distance between the two also. So this layer above could be any height. What you think that you are going to measure evaporation, say if this is your water body and you want to measure evaporation at this point. So this could be the vapor pressure of this layer and vapor pressure of this layer. So then we call this as vapor pressure gradient. So difference in vapor pressure gradient, vapor pressure per unit length. Per unit you can call as per unit distance. So let this distance be d. This is just like, Darcy's law. There you have hydraulic conductivity, which is basically the resistance, and then you have hydraulic gradient. Here we have vapor pressure gradient. This is the difference in the partial pressure of the laminar layer and the layer above it. So then resistance could be the resistance of this layer. For example, you are measuring over here, so water molecule has to move from this point up to this point. Now it will depend upon the resistance, and the main thing is turbulence. If there is turbulence, the resistance will be less, and again it will be the thickness of this laminar layer. So this resistance could be thickness of, it depends upon the thickness of laminar layer. More the thickness, more will be resistance. And this could also be because of the turbulence. If there is turbulence, yes, then the resistance will be less. If there is no turbulence, resistance could be more. So this depends upon the nature of the vapor flow medium. So in this case, the difference in potential evaporation and actual evaporation, this difference will be 0. So that means saturation, this is in fact the saturation vapor pressure, that is vapor pressure of the laminar layer, and this is your outer actual vapor pressure. This is actual vapor pressure. So in case of no turbulence, these two, saturation pressure and actual vapor pressure, they will become 0 and there will not be any evaporation. So so ultimately what we understand is that the water from a free water surface moves from liquid form to vapor form under two things. One is the driving force, that is vapor pressure gradient. There should be a vapor pressure gradient between the two. And second is resistance of the layer from which the vapor molecule has to travel. How much resistance it offers, and that resistance depends upon the nature of the flow medium, the thickness of the laminar layer, and ultimately the resistance caused by the turbulent layer. So this is what we understand over here. So under calm conditions, under no turbulence, there will not be any evaporation. And under normal conditions, the air movement, it will result in the mixing of the layers, and turbulence and convection. The water molecules, they may move through the process of turbulence. Convection could be there, and there could be decrease in vapor pressure. So because of the turbulence, the vapor pressure of this layer decreases and it becomes lesser than this, and then because of this VPG or VPD gradient, there is movement of vapor molecules from the water body to the outer atmosphere. Now, based on this, Dalton, a scientist called Dalton in 1882, he gave a fundamental law of evaporation. Dalton in 1802, he gave a fundamental law of evaporation. What is this fundamental law of evaporation? It is that because Dalton considered all these factors, the resistance depending upon different factors, and then the driving force. So he said that evaporation rate, I will call this as ER. This evaporation rate is equal to E0. And what is this E0? This is mean vapor pressure at the water surface. So this is mean vapor pressure at water surface. This is what is the mean vapor pressure over here. So this will be E0 at water surface minus ED. ED could be the mean vapor pressure at E. This is mean vapor pressure at any point. You can say at any point above water surface. So now this is basically the difference in the vapor pressure, and this is a function of U. And what is FU? It is function whose value depends upon the horizontal wind velocity. Depends upon horizontal wind velocity. So Dalton said that the evaporation rate, it will depend upon the difference of vapor pressure between the two layers and the horizontal wind velocity, because this will ultimately define the resistance as well as at what speed the water molecules or vapor molecules they move. So other factors remaining constant from this law, the evaporation rate is a function of wind velocity. And here let me give you a simple example. Even if the temperature is very high, no wind is blowing, your clothes which you have put outside after washing, they dry at a very slow rate. But on the other hand, if even the temperatures are low and wind is blowing, then the clothes, they dry very soon. And at the same time, sometimes people do that they move the cloth in this direction. The two persons, they just do this type of movement. They make the air to move, so they create sort of wind, and that results in this time by FU, and ultimately evaporation rate increases. So this is how the evaporation takes place. Now coming to evaporation from soil surface. This is what till this time we understood that how evaporation takes place. Now we will see that this was the evaporation at the soil surface. Now how could be the evaporation at soil surface take place? Now if this is your water body, this could be a soil surface, okay? So this is soil surface, and say assume that this is wet, and again there could be a laminar layer. This is laminar layer over here, as you have on a free water body. At the soil surface also we have a laminar layer, and again we have a then zone of transition where the density of molecules per unit volume is very low, and ultimately you have turbulent layer. Same process, but then what the difference is, now here first most important thing is that water molecules are attracted by soil particles. We have already studied, I have explained this in my previous lectures, that how water is retained. So if this is your water molecule, they are adsorbed on the surface of the soil, being bipolar in nature. So this is how they got. And the first layer of the water molecules which are attracted towards the soil solids, it could be attracted with a force as high as 15,000 atmospheres. And the partial pressure of the our atmosphere is 1 bar. So this could be attracted with 15,000 atmospheres or something more like that. So again the water could be adsorbed on the surface of the soil particles. It could be absorbed in between the particles, that is your pore space. So now this is that we call this as soil metric potential. So this is the force with which water molecules are attracted towards the soil particles. Now this is one thing. Otherwise the atmospheric conditions which are governing the evaporation from free water body are same as the evaporation from a soil surface. But the first difference is that the water molecules are attracted. So this is here there is free supply of water molecules. Here you may not have free supply of water molecules. So this is the second difference. There is no free supply of water molecules on soil surface until and unless the soil is flooded. And if it's flooded, then the evaporation, we will not say that it is taking from the soil surface, it is taking from a free water surface. So then this is going to be the process. But if you have a soil, normal soil, unsaturated soil, in that case there will not be free supply of water molecules. So then again, soil moisture content it decreases with time, and soil moisture content increases with time because of evaporation, number one, because of plant water uptake, and third, because of the horizontal or vertical movement into the soil. Water may move out of the root zone depending upon so many things we have already studied, that their water could move in horizontal direction, in upward direction, downward direction. So it's a very today we are just concerned with how water moves upward. But the question is when you are studying evaporation from the soil surface, so soil water content may go on decreasing with time. There could not be free availability of water molecules to get evaporated. So, and On the other hand, if you have a field, when I say field means with crop, soil with crop, then in that case evaporation is taking place from bare soil. We call this as evaporation. Evaporation is taking place from the plant canopies, so we call this as transpiration. And even in a field, the evaporation could be taking place from a free water surface. Though this is rare, but this could be a process, because sometimes, you know, when you irrigate the field, after infiltration, some lower spots, they have water standing over there, and then evaporation is taking place not from the soil surface, but it is taking place from the free water surface. So though this is rare, but this is very common. So here E and T, these are interdependent processes. If somehow you are trying to decrease evaporation by mulching or something else, then maybe that water may be diverted towards the transpiration depending on the atmospheric conditions. So these are very difficult to separate, these two components. So generally we call them as ET. We call them as evapotranspiration. So this is very important phenomenon, ET, you know, because ET directly governs the rate of photosynthesis. So now the question is, when water is evaporating from the surface of the soil, we need to have certain physical conditions. What are those physical conditions which are necessary for evaporation to take place? Physical conditions for evaporation. Because, you know, earlier in my lecture at the beginning I said that evaporation is movement from liquid state to vapor state, and water molecules, they are in motion, they have their kinetic energy, but their kinetic energy needs to be increased from that of the force of attraction by which these molecules are attracted. So to increase the kinetic energy, you should have sufficient heat energy, what you call as latent heat of energy. And this latent heat is 590 calories per gram. So that means to evaporate 1 gram of water, that means to convert 1 gram of liquid water to vapor form, liquid form to vapor form, you require 590 calories of water at 15 degrees centigrade, or you require 2.5 into 10 raised to power 6 joules per kg of water, again at 15 degrees centigrade. So this is the kinetic energy, this is the latent heat energy, and this latent heat its source could be from within the body itself, soil, because if soil becomes wet, so there is evaporation. Even if you don't have any energy coming from the atmosphere, the soil itself can it can use its energy to convert water to vapor form, from liquid to vapor form. So in that case, it could be within the body, evaporating body, or it could be the outer source. Generally it is the outer source. The energy coming from within the body is a small component, because everybody tries to be cool, even human beings. Our body temperature also tries to make a type of, we sweat, and when we sweat, then because of the turbulence, the vapor molecules are carried away and we feel a bit cool. So this is a process, same process. Soil also, if it becomes too hot, too warm, then it tries to release its energy. That energy is used if moisture is there. That's also important. So if moisture is there, it tries to evaporate the moisture, becomes cool, its temperature decreases. So this is first thing, first physical condition, that you should have sufficient heat energy. It could be through the outer sources, as I said, advective energy, radiate energy, like that. Then second important thing is there should be a vapor pressure gradient, or what you call as vapor pressure deficit, because this is a driving force. Until and unless there will not be any difference in the partial pressure of the two layers, evaporation will not take place. And we call this as atmospheric evaporativity. Or in simple words, we call this as atmospheric demand also. Atmospheric demand. So until and unless there is a demand from the atmosphere, evaporation will not take place. And simple example is that during the months in North India, during the months of April, May, June, the relative humidity of the atmosphere is very less, and because of that the evaporation rates are very high. But when we have the monsoon rains in July, August, September, relative humidity increases, evaporation rates, they decrease drastically, and that is the example that our ladies, they get very frustrated because they say that the clothes do not get dried soon. I mean at a faster rate as they used to get dry during the months of April, May, June. So this is because the evaporativity or atmospheric demand for the moisture is high during the monsoon period. Third thing is that of course for evaporation to take place, evaporation, as I said, it is the conversion of water from liquid form to vapor form. So evaporation will take place only when there will be continuous supply of water. So continual, since we are studying evaporation from soil surface, so I will say continual supply of soil water. Because if the moisture content in the surface layer dries, then continuously the moisture from the lower layers, it rises through the process of capillarity, reaches to the surface. So there is continuous supply of water at the surface of the soil for water to get evaporated. So this is called, if the soil is able to provide moisture content, then evaporation will take place. They call it as soil evaporability. That means ability of soil to provide moisture for evaporation. This is evaporativity, this is evaporability. So evaporability will be less where the soil moisture will be less. It will be higher if the soil moisture is high. Now coming back that under normal conditions, how the evaporation from the surface of soil takes place. So I should draw this also. Well, if I say that this is your relative evaporation rate, relative evaporation rate. Relative evaporation rate means E0 over EA. E0 is potential evaporation, means evaporativity of the atmosphere. The maximum evaporation that can take place at a particular atmospheric condition, at a particular atmospheric demand. And this is the actual evaporation. So the ratio of the two could be 1. Now, supposing that initially, this is time over here, this is time, this is relative evaporation rate. Now, initially your soil is say saturated, maybe even immediately after irrigation or immediately after rainfall, then the evaporation could be, it could be 1, it could be less than 1, it could be even 0.5, but it will not be, it cannot be higher than 1 because it is relative evaporation rate. So when it is 1, that means actual evaporation is taking place as per the demand. Whatever is the demand of the atmosphere, same is the actual evaporation taking place because there is no dearth of water. Now this is, this may go up to 2 hours, it may go up to 4 hours, it may go up to 2 days, it may go up to 2 weeks. So this is constant rate state, that with time the relative evaporation rate is not decreasing. It is taking place as per demand of the atmosphere. So after that, once, because it is getting this continuous supply of water, and once the supply of water decreases, there is abrupt and immediate decrease in evaporation. So we call this as stage 1, and stage 1 is called initial constant rate stage. Many a times we also call this as constant rate stage. We don't use the word initial. So here, because of continuous supply of water, the relative evaporation rate is taking place at a constant rate. It is not decreasing with time. But once the soil moisture decreases, there is abrupt and drastic reduction in the evaporation rate, and we call this as stage 2. Stage 2 is called as many times people call this as intermediate falling rate stage, but I will call it as falling or decreasing rate stage. And then you have stage 3. Stage 3 is extremely low rate. Extremely low rate stage, and ultimately the evaporation may be, it could be 0. I mean, there may not be any evaporation. Now the question is, at stage 1, as I said, because there is continuous supply of water, so whatever is the demand of the atmosphere, that is being met. Okay. So second stage, it is now, so stage 1 is governed by the atmospheric demand only. So stage 1 is governed by atmospheric demand only. But stage 2, because stage 2 evaporation rate decreases. Why it decreases? Because the soil is not able to supply water as per demand of the atmosphere. So that's why with time, with the decrease in moisture content. Now here, what could be the fall of this? Now here I have shown the steep fall. The fall could be like this also. Fall could be like this also. So that will depend upon at what rate the water is being supplied. So that rate or capillarity process, that will depend upon the profile characteristics. So stage 2, I should say, it depends upon, it is controlled by its profile control. Even if the atmospheric demand is high, even then the profile is not able to supply moisture to the surface, or does not supply moisture to the surface, because this is the process nature has made. So of course there may be some moisture in the soil, there could be some moisture for the plants to take up. So but there is very little moisture for evaporation process to take place. That's why this is called falling rate stage. And at rate 3, in this stage, the upper layer or evaporating surface, it virtually becomes dry. It becomes air dry. Air dry evaporating layer. So when this becomes dry, for example, this is your soil surface. So it becomes air dry, and the moisture content, it could be just 3%, 3 to 6%, depending on the texture of the soil. So when this layer becomes dry, then water molecule present over here, it has to move. When it enters into this layer, it has to be in vapor form. You know, so water from this point, point A to point B, it has to move in vapor form. So this becomes vapor movement of water. And if you remember soil water movement topic, I said that there is saturated movement of water very fast, unsaturated movement decreases, and third could be the vapor flow. The diffusion of vapor is very, very slow, so that's why this is stage 3, where the evaporation reduces drastically. And sometimes we also call this as self-mulch or soil mulch. Self-mulching. This is the process of self-mulching or soil mulching. So that means soil itself acts as a mulch and protects the water to get evaporated out. So that this way, somewhere the soil tries to keep its crop plants, water, it tries to keep water available to the crop plants. This is how, you know, the beauty of the nature. And that's why we call this as self-mulching or soil mulching. Ultimately, mulching means you are spreading something at the surface of the soil, try to reduce the evaporation rate artificially. But here the soil itself, because the upper layer, generally it's loose upper layer, it gets air dried, and there is then vapor flow of water, which is very, very slow, and evaporation virtually is very, very close to nil. So this is how the evaporation from the surface of soil takes place. I hope I am clear in making you understand the things. In our next topic, we will proceed further that how evaporation from the soil will take place when there is a shallow water table, and how it will proceed when there is a deep water table. So that will be in my next lecture. I hope to record it sooner than later. Thank you very much.